Log on, tune in, find out. Another good idea from Cambridge.
After computability theory, we now move to cryptography. Nigel Smart is one of our organizers. You have already heard that he is organizing 2 workshops as well, but he's also one of the speakers today. He is a professor at the University of Bristol, and he is also, this is something that we didn't mention. Well, we sort of mentioned it when Barry mentioned computability in Europe 2012. In addition to all of these smaller workshops, there are also a number of big events going on. So one of them is the Turing Centenary Conference leading up to Turing's 100th birthday. And another one is Eurocrypt, which takes place in Cambridge. And Nigel is the main organizer and probably the chair of the program.
No. I've separated our community.
Okay.
That's probably too much work.
Okay, Nigel will talk about modern cryptography for non-cryptographers.
Okay, so can everyone hear me at the back, yeah? This seems to be working. Okay, cool. Right, so a few announcements first. There are some books outside. They're last year's Eurocrypt. We've got a few left over. We're flogging them. If you buy them from a shop, they'd be 80 odd quid, right? That's 20 quid. That's a really good deal. Please give me your 20 quids and take a book. We've got gazillions of them. If you want to go to Eurocrypt this year in Cambridge, it's in April. It's going to be really good. The registration is now open. Now, you may not know this, but if you want to get money, cybersecurity is the place to go. There is so much money in cybersecurity, it is quite scary. And to help academics and people doing other areas of maths and computer science get into cybersecurity, we have a very, very, very generous grant from CESG, who is the crypto end of GCHQ, to sponsor people to go to this year's Eurocrypt who are young researchers in the UK. If you send me an email, I will be able to get you to get into Eurocrypt for free. It's quite expensive to normally go to Eurocrypt, so please send me an email. So we've got lots of stipends. Please see the Eurocrypt website. For those of you who want a bit more information about the Bristol Crypto Group, which is now the world's largest crypto group, we have our corporate brochures. I'm not used to mathematics audiences, so this is kind of a bit more corporate style. Blah blah blah. So we have that. Come. I've got loads of these to give out. Lots of nice pictures. Who's got married, etc., in the year. But to make sure that this is really is a mathematics talk and not some computer science talk, I have decided to use chalk. Okay. So this will mainly so I don't have to prepare anything. I'm going to assume that you know nothing about cryptography, okay? Because what we see in industry and in computer science and cryptography is that people come from a maths background, and almost all of the mathematics cryptography courses that are taught in universities, certainly in the UK, are stuck in the 1970s. So what I wanted to do is kind of introduce you to what modern cryptography is about, and hopefully I'm not even going to include an equation. Okay, it's all going to be with pictures. Ooh, oh no, I will have some equations, but they're not proper equations. Okay, so we're going to introduce, can we get rid of this? Probably a good idea. Okay, so I'm going to introduce some algorithms, and we're going to see what to do. So the first thing that you ever want to talk about in cryptography is symmetric crypto. Okay, so this program's called Syntax and Semantics. Now the first thing you do in cryptography is you define the syntax. Okay, so that's good. So what is the syntax of a symmetric encryption algorithm? Well, as I have an encryption algorithm, well, no, I'll start properly. I have a key generation algorithm, which takes some security parameter. I'm going to be a bit loose with stuff, with definitions if you're a real cryptographer. A key generation algorithm, which guess what outputs keys. I have an encryption algorithm, which takes a key and a message and outputs a ciphertext. And I have a decryption algorithm, which takes the same key, hence the word symmetric, C, and gives me a message M. Okay? That's what a symmetric key encryption algorithm is. Now, the question is what does it mean for a symmetric key encryption algorithm to be secure? We can't even start discussing cryptography until we know what we mean by security. Okay, now here's a rapid Crypto 101 undergraduate course in cryptography for computer scientists. I take a Turing machine, A. Oh, I've mentioned the word Turing, so I must be in the good books already, okay? So A is a Turing machine because it's an adversary, it's the bad guy. And A is going to play a game. Okay, so the game A plays is as follows. A is playing a game with a challenger, which is the environment, so it's everything outside of the machine. So the adversary, so the environment picks a key K from the key generation algorithm, and then the algorithm, our adversary A runs. It's a Turing machine, it just runs. At some point, it outputs two messages, M0 and M1, and M0 and M1 must have the same length, okay? You know, one can't be a tiny message, another one a big one, they both must have the same length. And then the challenger, what it does is it creates a ciphertext C star, which is the encryption of one of those random messages. It picks a bit B from 0, 1, okay? It creates a challenge ciphertext C star and sends it to the adversary A. The adversary A then sends back its guess B dashed as to what the original bit B was that the challenger chose. The adversary wins the game if B equals B dashed, and surprisingly he loses the game if B does not equal B dashed. Okay, now there's lots and lots of reasons why this is the definition, and the definition is essentially due to Shafi Goldwasser, who is our Rothschild. I keep forgetting the phrase. Okay, so this is what's called semantic security of the encryption algorithm. Semantics, brilliant. I've got everything in the first blackboard. Okay, so I've got that. Now, so this is what's called indistinguishability of encryptions, IND, or it's called semantic security. It's basically, can the adversary find any meaningful information about the message? It's not just can you decrypt the message, it's can you determine any meaningful information, and meaningful information is even one bit of information, whether it's message 0 or message 1. And the reason they're different, they have to be the same length, is because it's bloody obvious. If you send a small one, you can tell the difference from a long one. Yeah? If I send a 1-bit file and a 50 megabit file, you can kind of tell the difference. Yeah? Okay, so that's the game that the adversary's playing. So that's our definition. You can formalize it properly in proper maths, but let's just look at pictures for today. And then the question is what powers do we give the adversary? So the adversary can be given a number of powers. So he could be given, it's a symmetric key encryption algorithm, so he could be given access to an encryption oracle. Now this encryption oracle, he sends it a message M dashed, and he'll get the ciphertext back C dashed corresponding to the hidden key K. So that, if he has that, he has access to that's a chosen plaintext attack. He can choose plaintext and get ciphertext back. If we have a decryption oracle, he can send ciphertext this way, and he gets messages back this way, okay? And he can call these oracles at any point. He can call these oracles before he sends his messages, or between sending his messages and getting the C star back, which is kind of pointless, or he can send his messages to these oracles between getting the C star and getting and him deciding what B dash should be, okay? Now, there's obviously something he's not allowed to do, because otherwise the whole thing is trivial. He's not allowed to send the decryption oracle the C star, okay? Because if he did that, he could trivially win. He goes, I've got a decryption oracle, you give me a ciphertext, I decrypt it, I give you the answer. Duh. Okay, so this is not allowed. Okay, now, for obscure reasons, which I won't go into, but a very, very good exam question for undergraduates, it's not going out before our exam set, is it? I don't know. Okay, is that for this talk, we will ignore the fact in the symmetric encryption algorithm we've got an encryption oracle. So for our points of view, we'll ignore that case, okay? For a very technical reason, we won't go to. But the decryption oracle. Now, if we have the decryption oracle, we say that the adversary is working in a chosen ciphertext attack, because he can choose ciphertext to get them decrypted, and then the whole game is called in CCA. Okay, so this is the default definition for encryption security from the mid-1980s, from Shafi Goldwasser's thesis, okay? Now, well, not quite. That bit's Shafi's, and then there's other bits do the other CCA, but essentially. So that's symmetric encryption. And then the goal of cryptography in the symmetric encryption environment is to design cryptographic algorithms which meet that definition in some mathematical sense. Okay, so that's the mathematical definition of security in pictures. Okay, happy with that? Good, right. Okay, so we've done symmetric crypto, so the next thing is to do asymmetric crypto. So what's asymmetric crypto? This is public, private key stuff like RSA, like everyone kind of knows. So we have syntax. Let's do the syntax again. Well, here we have a public key and a secret key come from the key gen. Oh, I should say we need correct this, shouldn't we? You know, that if I decrypt the encryption of a message, I should get back the ciphertext for all choices of message and all choices of keys, yeah? But, okay, it's kind of obvious. Right, so I have a public key and a secret key. I encrypt with the public key, and I decrypt with the secret key. Okay? And I have correctness if for all choices, all outputs of the key generation algorithm, all valid messages, if I encrypt then decrypt, I get back M, yeah? So, hey, there's an equation. I lied. Okay. So what's the syntax? So that's the syntax for public key encryption. What is the security requirement? Well, okay, so let's just cheat and copy that. So Turing machine A, okay? Well, actually, the adversary actually is given some information now. The public key is public. So we need to give the adversary, at the very beginning, the public key. It now plays around. It comes out with two messages, M0 and M1. And the environment picks a bit B. It encrypts the message B, C star, and then the adversary picks a bit B dashed. Okay, now we're going to copy these oracles. Encryption oracle. Do we need an encryption oracle? Okay, someone understands. You have one. Brilliant. Yes, exactly. You have one. Because you have the public key. It's a public key encryption algorithm. Therefore, anyone can encrypt. So there's no point in giving someone a encryption oracle. Okay? But the adversary doesn't have access to the decryption oracle. Sorry, doesn't have access to a decryption algorithm. So if you want to model chosen ciphertext attacks, you give him a decryption oracle. He can input any ciphertext he wants, as long as it's not equal to C star, because that's just cheating and not playing cricket, okay? And then he gets the message back and he can play. So these are the two standard definitions for encryption. Now you could argue, one, does this make sense? Two, why is it like this? Okay, so does this make sense? Well, this indistinguishability makes sense, because imagine you are, I don't know, you're monitoring someone who's buying and selling stocks. If the ciphertext is only buy or sell, and you keep seeing, you know, the ciphertext goes along, it says buy, it is a buy, but you don't know it is, and then it comes over here, and this guy actually buys some stocks. And then this other ciphertext came here along, and this guy actually sold. Then you kind of deduced that what was going on, yeah. So these definitions imply something. What they imply is that the encryption algorithm for public key has to be randomized. Yeah? Because suppose you wanted to buy some stocks, so you send a message buy over to Benedict, and I see a ciphertext, okay? And then you buy something. If I see the same ciphertext again, I can deduce from the prior information that this was a buy order. But if the encryption algorithm is randomized, it's not. Yeah, I can't deduce this, because every message corresponds to a very, very large number of possible ciphertexts. The same ciphertext isn't going to occur twice. Okay, what other objections might you have? Okay, so that's an objection possibly to the indistinguishability game, which I kind of tried to convince you that that's not doesn't hold. So let's look at one for the possible objections for the decryption oracle. So you could argue that this definition of security is over the top. Why the hell would a user be so stupid that he gives an adversary access to a decryption oracle that decrypts stuff for him? Okay, that would just be mad, wouldn't it? Okay. Now, it turns out that actually the world is mad. Very, very early versions of SSL, which is the thing you use to communicate over the interweb, they essentially, when you could send the website a ciphertext that was complete rubbish, and the response coming back would tell you something about that ciphertext. So you could use this to this kind of, it wasn't a full decryption oracle, but it was kind of like a semi-decryption. You could use the website as a sort of semi-decryption oracle, and you could use this to recover the secret key behind whatever key the website was using, okay? So this was, early days of SSL, late 90s. So having a definition like this might look like overkill, but if we can design our algorithms so that mathematically they satisfy this definition of security, then if I put them in the real world, no matter how stupid the user is, we can still make sure they work correctly and still maintain security, okay? So the idea is having a definition that is so over the top in terms of security that it captures stupid users, okay, or mere engineers, okay. Right, so that's symmetric crypto and asymmetric crypto, okay, in a nutshell. And now you kind of go, well, how am I going to use this? Now, so symmetric crypto is, like if you went to a 1970s course, you would have heard it was called DES. Okay, if you go to a modern course, this is AES, except it's not quite. That's data encryption standard. This is advanced encryption standard. This is rubbish. This is good. But you'd kind of use the AES in a special way. So it's not just that you take AES and use it as a symmetric encryption algorithm, because AES only encrypts 128 bits, whereas sometimes I might want to encrypt a megabyte file, or I might want to encrypt a movie coming back from YouTube or something, okay? So that's what I would use for asymmetric crypto. But asymmetric crypto has symmetric crypto has one really, really good point going for it, is that it's fast in terms of performance, okay? Now the problem with symmetric crypto, which is why people invented asymmetric crypto, is that we have a key management problem. How do we manage all this? Symmetric key has to be on both sides, which is why public key crypto was invented, RSA. So how do I do asymmetric crypto? Well, again, if I'm in a 1970s course, I would have done RSA. If I was in a modern course, I would do elliptic curve cryptography, okay? That doesn't stand for error correcting codes, that's elliptic curve cryptography, okay? And these allow us to do efficient, secure, public key crypto. The problem is that they are slow. Okay, so with public key crypto, asymmetric crypto, we solve the key distribution problem. The trouble is it's slow. With symmetric key crypto, we have a problem in that we've got a problem with key distribution, but it's fast. So what do you normally do? What do engineers normally do? They put the two together. So that's what we're going to do. We're going to put the two together. Now, to put the two together, we don't actually use asymmetric crypto. Okay, so anyone who says, well, we use public key crypto, is actually, public key encryption is always lying. No one in their right mind, except in very, very obscure applications, uses public key encryption. Okay? What they actually use is they use what's called a key encapsulation mechanism. Because what I really want to use to encrypt stuff is the symmetric crypto, because it's fast. So what's a key encapsulation mechanism? Or KEM? Okay, so first we have to define the syntax. So what's the syntax? We'll have a key generation algorithm that's going to present a public key and a secret key. Okay? Now, what I do is to encapsulate, luckily also called enc, which is quite nice. Okay, I take the public key, I give it some randomness, no message, and it returns a key K, like one of those keys Ks, and a ciphertext C. The decapsulation mechanism, also called DEC, just to confuse you, okay, takes the secret key and the ciphertext, or encapsulation, and returns the key K. Okay, so this key encapsulation mechanism is a way of encapsulating keys. Okay? So it's not really an encryption. Okay? This is actually a simplification. This simplifies things, which means you can design more stuff. It might look a bit weird to start with, but it is actually better. Okay? Okay, so what's the security gain? Okay, so the security gain for a chem is as follows. We take our adversary, the Turing machine A. Oh, it's always given the public key at the beginning. Well, output 2 messages, that doesn't make sense, yeah? So it doesn't output 2 messages. Okay, so what happens is the environment picks a bit B, the environment runs and gets C, let's call it KB C star from the encapsulation algorithm with respect to the public key with some randomness R, okay? And it's also going to pick a random key, K1 minus B. Oh, actually, no, let's make this simpler. Let's call that 0. Let's call that 1. And it generates a random key from the key generation of the symmetric algorithm. So it picks 2 symmetric keys. One comes from the encapsulation algorithm, and one comes from the key generation algorithm of the symmetric encryption algorithm, yeah? And it gives back C star and KB. So in other words, in the chem security game, what we have to do is distinguish between if the bad guy's, what's the bad guy's goal? The bad guy is given an encapsulation C star and a symmetric key and has to determine whether that symmetric key is valid, in other words, it corresponds to the C star, or it's complete nonsense. In other words, it was chosen randomly, independently of C star. Okay? So it's a real or random game. Okay, and then what things can we give him? Well, we can give him a decapsulation oracle where he sends it a C star and it sends back the key K. Well, gives him a C, which is not equal to C star. You kind of got the gist by now, yeah. This is always the same thing over and over again, and that's what we give him, yeah. So this is the key encapsulation security game. Okay. So, how do we put these 2 things together? We kind of do it in a trivial way. To actually construct a public key encryption algorithm, what you do is you take a chem and you take one of these symmetric algorithms, which is actually called a DEM, a data encryption algorithm, what's called the chem-dem way of constructing encryption. And this is what most systems actually do, deep down somewhere. Okay, so you generate the public key and the secret key. For the public key encryption algorithm are actually the key generation algorithm of the chem. To encrypt a message M with randomness R, what you do is you generate a key with the encryption algorithm or encapsulation algorithm of the chem with the public key of the randomness. This gives you a symmetric key, and which way did I put it round? K and a C. K and a C. Let's call it C0. Okay, and then C1 is I do the encryption algorithm of the symmetric key, encryption algorithm of the message, and I output C0, C1. Okay? So to decrypt, what I have to do is I take C0 and C1. I use the chem inverse algorithm to construct the key from the C0, and I decrypt the big message with the C1. So this gives me the best of both worlds. It gives me the speed. If I'm encrypting a megabyte or gigabyte of data, I have the fast algorithm to encrypt the gigabyte of data, but the slow algorithm to encrypt the key. So I solve the key distribution problem with C0, and I solve the ability to send and decrypt large amounts of data with the C1. So it seems to be brilliant, yeah? Well, at least someone say yes. Okay, right, so it seems to be brilliant, okay? Yeah. Right, now, the question is, does it work? Is it secure? Can we prove it works? Okay? Right, so hand-wavy proof. You can make it very formal, it just takes ages, will bore you all to death. Okay, so I want to prove that that construction meets that definition. that construction over there is a public key encryption algorithm. Therefore, its security definition is the one at the top. Okay? So let's assume that the components I am using satisfy this security game and this security game. Okay? So I have to prove that that construction meets that game. So I'm going to do this by what's called game hopping. So I'm going to call this, have I got colours? Brilliant. Can you see blue at the back? Yeah, good. Okay, so let's call this game G0 is the, well, okay, let's instantiate it a bit first. So this C0, C1, this gives me a C0 star, C1 star. And what is C0? C0 is the encapsulation with respect to the chem of some random stuff with respect to the public key. Okay, and this also kind of outputs a key K. Yeah, and this one here is the encryption with respect to the symmetric algorithm with respect to the key K of the ciphertext of the message M. Yeah, MB. Okay, so that's my two things. And let's call that game 0. Okay. Now, game 1 is I'm going to modify slightly. So game 1 is going to be in blue. It's going to be different, yeah? So what I do is I run exactly the same game. I'm running the same adversary, the same Turing machine, but I'm going to run him in a completely different environment. And I'm going to change the environment in one particular way. The way I change the environment is that instead of choosing the key K there, white, which was valid, I'm going to choose it invalidly. And then when I encrypt, I'm going to encrypt here with respect to the invalid key. Okay? So if in the game G1, the adversary is running in the wrong environment, okay? So we have no clue really what it does. Because if I run a program, it's like taking a program that runs chess and then running it in an environment where it expects the moves to be drafts. Okay, you're just going to get rubbish out, it would appear. Okay? So the goal is to actually prove you don't get rubbish out. So let's look at this for a minute. What happens in the blue environment, in the game G1? Let's just look purely at game G1. Well, in game G1, the encapsulation at the beginning, the C0 star, is completely irrelevant. Yeah? It's completely irrelevant to the adversary. So if the adversary was running in G1 and he managed to guess which bit was correct, yeah, he must be doing this because he's breaking the C1 star. Yeah? But if he's breaking the C1 star, he must be breaking the symmetric encryption algorithm. Okay, so you have to be a bit more careful about this. So what we have to do is we have to do complexity theoretic reduction. We have to say, let's assume we've got an adversary that wins the blue game, and from that I'm going to construct an adversary that wins this game. Okay, now if you ignore the decryption oracle, that's trivial. Yeah, that's 40% in an exam. Okay, that's passing the exam, almost. Well, okay, that's only half the question. So it's 20% in the exam. Okay. Right, so the only thing you have to worry about is the decryption oracle that we give this guy here. So he has, but C star is actually C0 star, C1 star. So he could give the bad guy C0 star, comma, something not equal to C1 star, or he could give it something C1 star. Okay? So what we do is to construct the reduction down to this algorithm. We generate our own public-private key pair because the chem's irrelevant. And then we can always answer queries on the first coordinate because we know the key, except for this one, where we use the DEM oracle, the decryption oracle, for the symmetric key algorithm, which we're given here. Okay? So we have to kind of play around a bit. Okay? So I'm not giving you all the details, but you can look them up in the book. Okay. And otherwise, if it's on video, Bristol students are all going to pass their exam, aren't they? Okay. Now, so that's game 0 and game G1. So if we can, the point is that if we can break G1, that implies I can break the symmetric algorithm. Now, what do I mean? What do I really want to prove? I want to prove that the probability of breaking G0 is as small as possible. So really, I just kind of do, I do my kind of like a, I want the probability of winning in game G0. Well, by the triangle inequality, this is essentially, this is G0 minus the probability of winning in G1 plus the probability of winning in G, well, not by the triangle inequality, just by bloody obviousness, that's equal to, okay? And then by the triangle inequality, I have okay. So what I've said is that if the adversary's running in game G1, he can't win because he would break the symmetric algorithm. So I know that's tiny. Okay, I can formally define tiny, but let's not worry about that. So what I want to show is this is what I want to show to be tiny, and tiny plus tiny is tiny. So what I want to show is I want to show that this bit is tiny, in that the adversary, when running in game G0 or running in game G1, he cannot tell which game he's running in. Okay? That's what I really want to show. Okay, so let's look at this a minute. So I'm either running in a game in which the key is valid, or I'm running in a game in which the key is invalid. Does that remind you of something? That's the chem security definition. Yeah? So, okay, so I have to play around with the decryption oracles and make sure that, you know, I get the right thing and set things up and kind of do things. But, you know, it's kind of intuitively obvious. So if the chem is secure, in other words, the probability of distinguishing between a real key and a random key is tiny, then the probability that the adversary can distinguish between game G0 and game G1 is also tiny. So that's tiny, and tiny plus tiny is tiny. So we are kind of done. Okay, so that does work, which is nice. Okay, so where am I? Have I got till 3, yeah? Okay. So so what I want to push on to now is I actually want to define how we're going to construct a chem. Okay, constructing symmetric encryption algorithms, that's like a whole different kettle of fish, but doing chems is relatively straightforward. Everyone's seen RSA before? Everyone know what RSA is? Yeah, okay, brilliant. So we have C equals M to the E. Okay, right. This is how you'd use RSA in the real world sometimes. What I'm going to do is I'm going to construct RSA chem. So what do? Well, I generate a public-private key pair, which I do normal way. And now to encapsulate, that's the chem encapsulation, what I do is I pull some random message, random RSA message. I form the ciphertext, which is R to the power E, mod n. But it's a chem, I output the key. Now I don't output R. What I do, my key is going to be the hash of R. Okay? So I never actually encrypt a message, I just encrypt random stuff, and then hash it to a key, then that key gets used in the symmetric algorithm, and I encrypt a large amount of data. Okay? So I want to show that construction, am I going to be able to do this? Can I actually remember how to do this? Yeah, vaguely. Okay, I don't have to pass exams. Okay, I want to show that construction meets our security definition for a chem. Okay, so how would I do this? Well, okay, so here's the adversary. And he's going to be given the public key, which is N and E in this case. We are going to pick some random stuff. We're going to form the ciphertext C star, which is R to the E mod N. And then we're going to hash R. That's going to give us K0. We're also going to pick K1 at random. Then we're going to give this guy KB and C star. and we can give him access to a decryption oracle. Okay. If you can prove it in that model, you're a genius. Okay, you really are a genius. You will. Yeah, that would be really amazing breakthrough. Okay. In fact, you could probably prove you can't prove it in that model. Okay, so RSA Chem is not secure in that model. So he has to output a bit B dashed. Okay, so here is where cryptographers cheat. Oh, we can't prove it in that model, so let's change the model slightly. So if you prove it in that model, you're proving it in what is called the standard model of computation. What you see in cryptography papers is, or in cryptography standards, is sometimes they use what's called the random oracle model. Now, the random oracle model means that the Turing machines have access to a function which behaves like a random function. Okay? So there is access to some random oracle, which is what we model the hash function by. Okay, so the hash function is modeled as a random function. Now, okay, so what does this kind of mean in terms of reality? Okay, imagine the algorithm A is actually a program. So the program makes function calls to a hash function. Yeah. Now let's assume that hash function is in an externally linked library. So all that we mean in the random oracle model is we intercept all the calls to the hash function, and we can interject whatever we want as back, as long as the bad guy can't tell what we're sending back is not what the real evaluation of the hash function is. It's just a random response. Okay. So in other words, the adversary works in an environment where he doesn't know the internal code of the hash function. He just knows it behaves like a random function. Okay. And then you go, but that's rubbish. And cryptographers go, yes, we know. Okay, but that's the best we can do. Okay, so if you work in this what's called the random oracle model of computation, which you can kind of justify in terms of these, software libraries, adversaries work in the software libraries. People who break public key algorithms don't really understand hash functions anyway, so they're like that. So we're going to prove it secure here. So what we do, we're going to construct an algorithm B which is going to break RSA. B breaks RSA. What's it given? It's going to be given N, E, and Y, and it's going to output the mathematical solution Y to the 1 over E mod N. Okay? That's just solving what's called the RSA problem. Extracting ETH roots modulo a composite is believed to be computationally hard. So we're going to construct an algorithm B that uses A as a subroutine. But A is going to have two subroutines itself, a decryption oracle and the random oracle. So B has to provide the answers to A's calls. Yeah? So what B does is that, okay, so the N and E come in from B. Boom, he does that. He's going to send C star is going to be always equal to Y. Okay? And every time A does a hash function call, B is going to just return some random piece of nonsense. Okay? So every time we do a hash function call, we do a random piece of nonsense, and we maintain a list which is the hash input and the hash output. And that's how B models this random oracle. He just maintains a list in his memory of these things. So every time A calls the same hash input, B always responds with the same hash output, so it is a function. So A can't see that it's not a function. And every time A asks for a new input, B comes up with a new output and responds. Okay? Now, we've got this decryption oracle. Now, the decryption oracle is, what's it going to do? Well, the decryption oracle is going to has to kind of keep some maintenance of stuff going on. So the hash list not only contains hash input, okay, but also he also maintains hash input to the power E mod N. Okay, so every time you call the hash function, you store hash input, the random output, and hash input to the power E. Because then, when the guy calls a decapsulation query, you can see whether it was here, and therefore respond with the right hash output. Or if it's not on this list, you create a new value for hash output and hash input, and then you have to maintain consistency. B has to maintain consistency between the two oracles. Okay? So A can't tell it's being fooled. But that's quite, that's just bookkeeping. So you have to do a bit of bookkeeping in the proof. Okay, so that's how we're going to construct B. That's basically algorithm B. And at some point you actually interject Y into one of these things. So how is this going to work to solve the RSA problem? Well, the idea is as follows. Suppose A runs, and in this game that is being fooled by B, it outputs the correct B. If it does this with a significant enough probability, then at some point on its hash list, it must have asked for the hash input. In other words, it must have asked for e to the y 1 over e, y to the 1 over e. So in other words, on the list which it's maintaining for the hash function, it would have actually asked for y to the power 1 over e. So because B knows this list, it just goes down it and goes, oh yeah, there it is, boom, that's the output. Yeah. So with high probability, if A wins with high probability, we can map that into B winning with high probability. There's all sorts of bells and whistles and equations you have to put in here to make it all work, okay? But that's the basic idea. Right. So that was symmetric. That was just how you encrypt. So in the last quarter of an hour, I'm going to link this to all sorts of other things that's going to happen in the program. So this is a complexity theoretic reduction. This is what we call provable security. Provable security is you define a security model, you define something you want to achieve, the public key encryption algorithm, you then prove that your construction meets the security model by a mathematical reduction, okay, by a complexity theoretic proof. And that's what's called provable security. And if you want to do anything in cryptography these days, that is what you have to do. If you do not do that, your paper is instantly rejected as rubbish, okay? It's just kind of like, I don't know, it's a bit like, I don't know, I can't think of another area that's like that without offending people, but okay. So it's just like what we do, okay? Now, that's one way of doing cryptography. That's one way of doing security analysis. And for basic level primitives like encryption signatures, MAC functions, blah, 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 very, very simple things, this is default. The proofs are rather horrible, and they're all generally done by hand. Now, there's another way of doing things that has been quite prevalent in the United Kingdom, which is to use logic. Now, in logic, to analyze big complex protocols, like a payment system or something, what they do is they treat things as symbols. So they might go, okay, I've got some protocol, I've got party A, party B, and A is going to send to B, B is going to send to A the ciphertext, which is the encryption of some message, okay, and then B sends to C, and then A sends to C, K, and then, look, K, the C can now compute M, yeah? It's symbol pushing. Okay. Now, if you have this symbol pushing, security is purely defined on the basis of, can you derive via the equations the values, the symbolic value of what is going on? So C can derive the message M because it's given C, it's given K, and via the equation of correctness, he can now recover M. But with any other symbols, with any other in this equational theory, there is no other way of recovering M. So unless A actually gave to C the key K, you would conclude that there is no information that can leak from this protocol. Okay? The problem is that it assumes that encryption is perfect. Okay? Whereas the provable security model, which is actually trying to model the real world, doesn't assume encryption is perfect. It's working with Turing machines. I've hidden here huge amounts of probability. The messages being sent along are real, genuine bit strings. We allow the Turing machine to do arbitrary bit manipulations, yeah? Anything it wants. It can run any polynomial time algorithm, probabilistic polynomial time algorithm, okay? Whereas in this equational theory, you can only deduce things which follow from the equations. So this approach is what's called formal methods. Now, the formal methods is very, very popular in the UK for analysing security protocols. It is not very popular amongst cryptographers for analysing security protocols because it basically hides all the information. A formal method proof basically says the formal system cannot discover any attacks. It doesn't actually give you a proof. It just says there are no attacks. Okay? So, downsides is it's not precise. Okay. Okay, so let's go positive and negative. So we have this provable security approach, which is precise. Okay. So we have one positive, one negative. The benefit of formal methods is it's automatable. You can have automated theorem provers, handcrafted, which is a negative. Well, it depends if you want to keep people in jobs, I suppose. Yeah, okay. So we will take it as a negative that handcrafted proofs are a pain in the arse to do, yeah? So we have something over here which is, just press a button and go. Well, it's not quite like that, but that's the theory. Press a button and go, but it doesn't actually give you what you want. And this gives you what you want, but it actually involves highly paid people spending hours doing things, yeah? Which is really good, but that's not really what we want, okay? Now, what we want to do is merge these two together. So we would call this is the area of meaning. This has semantics. This is the meaning of purely mucking around with symbols, yeah? This is just syntax, yeah? This is boring. Okay, from my point of view. So what we would like to do is get semantics and syntax together, okay? And this is kind of happening. So there's this area of so this is happening in two ways. We can go this way or we can go this way. So one thing would be is to enable the proofs in quotes that we do in formal methods, or the procedure we do in formal methods, when it's completed, to have meaning in the computational world. So this is symbolic world, this is the computational world. So we would like the process that happens over on this side of the world to have meaning on the left-hand side of the world. Now, theorems which allow that to happen are what's called soundness theorems. They're called more computational soundness. In other words, it allows you to map over results. So the things that happen here are computationally sound. In other words, if a theorem happens here, then it's true over here, which would be a good thing, because then we can use all the automated tools. The problem is the stuff we can map over is very limited. Okay, there are kind of big problems in the way of mapping all sorts of things you would like to do in security over. For example, commitment's a bit of a problem, and a lot of protocols use commitment. Okay, so a commitment is when it's like an encryption, but which doesn't have a secret key to it. So it's just like it's like I'm picking cards. Yeah, pick a card, any card. I choose my card and I commit to my card, and then to reveal the card, I just put the card on the table. Yeah, that's a commitment scheme. So commitment's actually quite hard mapping from here to here. So that's one technique. Okay, so computational soundness is one way of doing this, and that's been quite popular. We got in April, whenever it is, we can have lots of talks on that. The other way, which is beloved by the French, there's loads of people in France doing this, is that you take the formal methods approach and map it over to the computational world. Now, what do I mean by the formal methods approach? I just mean the fact you can automate the proofs. Yeah. So you try and get these automatable proofs to replace the highly paid cryptographers over on the left-hand side, yeah? And that's actually quite successful. So this chem-dem proof, I gave you, yeah, that if you take a chem and a dem, you put it together, you get a public key encryption algorithm, which I kind of gave you a sort of vague proof. If you actually do that by hand, you do it all formally, it'll probably take you 3 pages of A4, yeah, in LaTeX, yeah. I've got a feeling they could do this automatically, and it takes many, many, many pages of output of the computer. Okay, so it does. So the computer can produce the proof with some hints, just automatically, and check everything, check all the probabilities, etc. So you can kind of do it backwards. So there is a lot of stuff at the moment trying to merge these approaches together. Generally, because we know the formal methods has a serious problem, but people, in terms of it's not precise, and you can show things are okay in the formal methods world that you then break. Okay, so it's really not precise. And then in the provable security world, we want to analyze really, really complicated protocols now. We want to analyze the mobile phone system, VoIP, we want to analyze, TLS, everything. But that's just going to take too many man hours. It's going to take many, many PhD students of work. It is many PhD students of work just to purely analyze TLS, which is like the most moronic protocol on the planet that we have to securely log onto a website. No one knows whether we log onto a website correctly, cryptographically. It's just kind of like, well, we think so. Yeah, it kind of works. Yeah, we think it's okay, but there's subtleties there. So that's one version. So this is something we're going to be looking at. So that's one version of proof. Now, proofs in cryptography also come in a completely different way. So this is my final thing, which is another thing we're going to be talking about in April. So one of the key inventions in cryptography is from the 1980s is what's called zero-knowledge proofs, another invention of Shafi Goldwasser. Okay, so and Silvio Micali. So what we have is a zero-knowledge proof is the easiest way to see this is that let's look at NP and P. Okay, so what's P? Well, P is the set of all statements for which we have a witness that we can generate the witness quickly. Yeah. So the witness is a proof that the statement is valid. Okay. So in other words, P is the class of all statements that you can set as exam questions, because it's very easy to come up with a proof. Okay. Now, NP is the set of all things that you can check quickly. So it might take, you can't, coming up with the proof takes a great deal of effort. Yeah, because that's an NP, it could be an NP hard problem, but checking the proof is easy. So NP is the set of all things that you can submit to a journal. Okay, because it's the set of all proofs that can be checked quickly. Okay. Now we know that if we allow randomness, we can do more stuff. Yeah. Yeah. Randomness allows P to get bigger. We also know that if we allow interaction, if I'm giving a lecture and I'm meant to be interacting with you. Yeah. So if we allow interaction, we can prove much more complicated things, yeah? I'm the all-powerful professor at the front, you're just the mere minions, and by interacting, you ask me questions, I can then convince you of the validity of a statement, yeah? This is IP, interactive protocols. This is a much bigger class. Now, but as a lecturer or as a professor who's very well paid, I don't want that to happen, okay? Because then you become as well paid as me, and the value of my salary will decrease because there'll be more people of the same standard, yeah? So what we really need in lectures is what's called a zero-knowledge proof, okay? Where you leave the lecture completely convinced that I understand everything I've talked about and it's all correct, but you cannot reproduce it. Okay, so that's a zero-knowledge proof, is that you cannot reproduce my knowledge, okay? So in particular, we have some statement, let's call it S. We have some witness to some statement, which gives true, and the prover is infinitely powerful and he has knowledge of the witness, and the verifier wants to know whether the statement is true or false, and we allow him to interact, okay, but we want to deduce at the end that the verifier must verify that the statement is true. If it's true, let's assume the input is true, statement is true. And we must also verify that the prover knows the witness. Okay? But the verifier learns nothing else. So to me, this is a perfect graduate level lecture. Okay, so this is exactly what we should be aiming for. You should be convinced that everyone in front of you is very, very clever, but you have to go, if you go away and you go, well, I heard Nigel talk about this, but you'll have to pay him to reproduce the lecture for you. That would be my perfect, I have a business model to keep me in business even after they've done all this automated, yeah? Okay. So what this opens up questions is, how do we define this? How do we define that P knows something and V doesn't know something? V learns nothing, so he knows nothing else, yeah? But P, we have to verify that P actually knows something. Okay. So a zero knowledge protocol has 3 properties, which is completeness, that the thing is valid, soundness, which in the case of this is a proof of knowledge, in other words, the prover knows W, knows the witness, and zero knowledge, in that the verifier learns nothing else. Okay, now, I've only got 5 minutes, so soundness is proved by constructing something called a knowledge extractor, which I don't have time to define. So, but for every protocol, you can define a knowledge extractor, which has rewind access to the prover. And if you have rewind access to the prover, you can then run the prover many times and basically extract the prover. It might be a case that the prover doesn't even know he knows W, but even the fact that he interacts in the protocol means that you can still extract W from him by this knowledge extractor. And to prove the zero knowledge thing, we have to come up with what's called a simulator, which basically says that anything that the verifier could learn from the prover by interacting with the prover, he could have learned himself by faking interactions. Yeah. So the interaction tells you nothing. It's actually the process of interacting which gives you something. Okay, so all good lectures should end with an exam question. So here's the exam question for you, which is the default zero knowledge protocol. So this is a proof. This is what cryptographers mean by zero knowledge proof. I have prover, which we call Peggy, and verifier, which we call Victor, just to make a change from Alice and Bob. Okay, Peggy is going to know X, and Victor is going to know G to the X. Y equals G to the X. Okay. What Victor wants to know is, does Peggy know X? This could be authenticating yourself into a building. This could be next generation chip and pin card, okay? And we've got some group, so G, some finite abelian group generated by G. So just so I get some equations into the end, okay? Right, so what does this protocol look like? This is what's called a sigma protocol. It's a 3-round protocol. The first round is that Peggy sends R equals G to the K over to Victor. Or let's say the number of elements in G is Q, which is prime, okay? Victor generates an element integers mod Q and sends E back this way. This is what's called the challenge. And then the response that Peggy sends is S equals, how are we going to do this? I always kind of can't be bothered to work it out really. K plus X times E, doesn't really matter. Okay. So he sends them that way, and then to check the proof is valid, what Victor does is that he checks that G to the S is equal to the thing that was first sent times Y to the power E. Okay. So that is a zero knowledge proof that Peggy knows X. It's used in all sorts of things. Cards, not current chip and pin cards, but the proposal is this might be used in future chip and pin cards. It's used in all sorts of different things. It's clearly simulatable because, so I'll give you half your exam question in that Victor can produce a simulation of this without actually talking to Peggy at all, because it's important that you generate the challenges in that order. You go commitment, challenge, response. If you did E at random, S at random, and then fixed R from that, you'd come up with a transcript that was identical to a valid transcript, but was computationally indistinguishable, yeah? Or just indistinguishable, it's the same. So it's easily simulatable. So this is clearly a zero knowledge protocol. So the exam question, because I have not got time, is that construct the knowledge extractor for it. Anyway, there we go, I'll finish. But that's another type of proof that we have in cryptography. And from that, you can define signature schemes, you can define voting schemes, you can define all sorts of weird and wacky protocols. Thank you.
A few quick questions. No one seems to have any questions.
Good, thank you.
That's good.
Oh, tomorrow, 10 o'clock, Microsoft, there's a talk on fully homomorphic encryption by someone from Microsoft, I was told this morning. So if you're interested in encryption, go to Microsoft tomorrow morning.
Microsoft.
Yeah.
Okay. Well, I should also say, before we thank Nigel again, that there will be a Spitalfields Day picture taken in this following break. And we will, well, I was expecting someone to be here to lead the way. So why don't you all wait in this room until I get the photographer? And so let's thank Nigel once more.